Thank you, Felicitas, for this kind introduction. I don't very often these days give talks to large conferences like this. In preparing my talk, I was reminded of the very first large conference I went to. I was a young PhD student. In fact, I had just joined the lab, the metallurgy department in the University of Oxford in October 1959, and my supervisor, Professor William Hume Rothery, took me to a conference in Cambridge, and this took place in the Market Hall in Cambridge. The introductory speaker was Lawrence Bragg. Now, Lawrence Bragg had received the Nobel Prize for Physics in 1915, so he wasn't a young man. And I have this memory, I was sitting fairly far back, of seeing what appeared to be this old man staggering up to the podium, and then he looked at the audience and said in a slightly high-pitched voice, "Never underestimate the pleasure you give an audience by telling them things they know already." I've always tried to do that. I have a problem today in front of you. First of all, I did not receive the Nobel Prize in 1915 or any other time. And secondly, in telling you things you know already, I have to be careful because you all know much more than I do about every aspect of this subject. So, having said that, I will now launch into what I'm going to say. So, as Felicitas has already said, on the afternoon of the 13th of October, the 13th General Conference made the historic decision to adopt an atomic definition of the second. Now, I thought when I was preparing this talk, I would give an overall view on a couple of slides of the field. I quickly abandoned that because it is much too complex to do that. The main thing I will be talking about, and the thing which interests me most, are clocks. But in order to just give a little bit of background, I just mention some of those organizations that are involved in all of the activities that you do. Some of these I will mention later on. Of course, the Metre Convention, which Felicitas has measured, is the one I know more about. The Bureau International de l'Heure took a very important part in this. International Astronomical Union, also an extremely important part. International Earth Rotation Services, International Union of Geodesy and Geophysics, and so on. All of these bodies and unions and institutions are and have been of great importance. Now, I thought it useful to say, who does what now? And who did what in the old days? Now, as long as time was purely local, it was set by the rising setting of the sun, with the solar day being the basic unit. In the middle of the 18th century, John Harrison transformed navigation at sea by his accurate seagoing clocks. This is my own personal take on the history of time. In the 19th century, the building of railways and the invention of the electric telegraph led to time coordination within individual countries. And then in 1884, the International Meridian Conference in Washington established Greenwich as the prime meridian, and Greenwich Mean Time, GMT, became a universal reference. And at the beginning of the 20th century, radio, time, and frequent transmissions led to the creation in 1912 of the Bureau International de l'Heure at the Paris Observatory. Now, the unit of time, the second, had become established during the 19th century, first by Gauss with his millimeter, milligram second system, and then later in 1874 by the British Association for the Advancement of Science with their CGS system and later MKS. The second was being defined as 1 upon 86,400th of a mean solar day, and its realization being and diffusion being the responsibility of astronomers. Now, of course, the metric system created at the time of the French Revolution did not include a unit of time, only length, mass, and volume. Time remained firmly in the hands of the astronomers, but it might not have done. It might not have done. When the metric system was being prepared, the key decision was made by a committee of the Academy of Science made up of luminaries of the time, Borda, Lagrange, Laplace, Monge, and Condorcet. And they met at the Academy of Science on the 19th of March, 1791. 19th of March happens to be my birthday. It was a Saturday. My birthday was also a Saturday, but not, of course, 1791. And they sat down and they wrote a document which began, I will read it, I will give you my translation into English. The idea of referring all measurements to a unit of length taken from nature was seized upon by mathematicians as soon as the existence of such a unit and the possibility of determining it became known. They saw it as the only way to exclude all that was arbitrary from a system of measurement and to conserve it unchanged so that no event or revolution in the world would cast uncertainty upon it. They felt that with such a system, belonging exclusively to no one nation, one could hope that it would be adopted by all. Now, those are sentiments, I think, with which we would all agree. And those are sentiments that I can say, with the redefinition of the SI that I hope will take place in 2018, we may finally have accomplished this. But having said that, they then went on. The next two paragraphs, my translation, one can reduce to 3 the units that seem most appropriate as the base. The length of a pendulum, the quarter of the length of the equator, and finally the length of a quarter of a meridian. The length of a pendulum has the advantage of being the easiest to determine and in consequence the easiest to verify if some accident happens that renders it necessary. Furthermore, those who wish to adopt this measure already adopted in another country or having adopted it wish to verify it would not be obliged to send observers to the place where the original was established. In addition, the law of the length of a pendulum is well known, confirmed by experiment, and can be used without fearing small errors. Again, I think most of us would agree with that. But as is very well known, they didn't do this. This was the first 2 pages of this report. By the time they got to page 15, they had completely turned round and they had decided that the pendulum was not the best way, ostensibly because it brought in another unit, time, they said was arbitrary, because the splitting of the length of the day into seconds was an arbitrary decision. This is almost certainly not the real reason. The real reason, almost certainly, is that one of the members of the committee, Borda, had invented a dividing engine that would allow him to do surveying, angle measurement highly precisely, and he wanted to use this. And he persuaded the other members of the committee that they should in fact adopt 1/10,000,000th of the quadrant of the Earth. And this is the statement that's made by Delambre, because Méchant and Delambre were the 2 people who actually did the measurement. This is what it said in his book. But having decided that, they said, and it was formally adopted by the Assemblée Nationale, they should make a pendulum just in case anything happened to the meter that they were going to deduce. So they built this pendulum in the basement of the Paris Observatory. Sadly, no trace whatever is left of it. And they set up a pendulum. They could measure the time and the length as a way of maintaining a unit of length. Now you remember, 1791, this was after Harrison and others had made clocks that were extremely good. Now in the book by Delambre, taken from Base du Système Métrique, he gave a set of data that he obtained with this pendulum, and I looked at it carefully, and I deduced that the relative standard deviation of the supposed lengths that he was measuring was about 5 parts per million, which is orders of magnitude better than what they obtained with the units based upon 1/10,000,000th of the quadrant of the Earth. So I think had this been adopted, time would have come into the metric system much earlier. The first formal treaty concerning measurements was the Metre Convention. That was in my very first slide, whose mission was, and this is written into the convention, to assure the international unification and perfection of the metric system. Thus, it did not include any responsibility for the unit of time. The scope of the Metre Convention of 1875 was enlarged by a second convention in 1921, but still this did not include any specific responsibility for the unit of time, although it left it open to member states to extend its range of responsibility as necessary. Now, many of you know that, I've already mentioned it at the beginning, the Bureau International de l'Heure was set up in 1912, when it became clear that with radio transmissions, there needed to be some coordinating organization. So why was it, with a convention already existing concerning measurements, that no one thought that the responsibility for time should be with the Metre Convention? I have no answer to that. I've looked at the papers that took place, looked at the meeting reports of the International Committee for Weights and Measurements and the General Conference in 1913, which took place in Paris, all of this taking place at exactly the same time, including people in the academies of science that were at a high level, and there's no mention whatsoever of the possibility of the Metre Convention including time. I don't know the answer to that. The Metre Convention first took formal responsibility for the unit of time only in 1960, with the creation of the International System of Units, SI, considered to be the modern form of the metric system. The SI included the second, which was also redefined in 1960, as Felicitas has said, as the ephemeris second. I will come back to that in a few minutes. In 1985, the Metre Convention took over responsibility for the world's timescale, TAI and UTC, from the Bureau International de l'Heure. And the other half of the BIH responsibilities became the International Earth Rotation and Reference System Service, IERS, a service of the IAU and IUGG. I mention all of this to again, give you the background. The IERS is responsible for providing information required to relate terrestrial and celestial reference systems, including time-varying measures of the Earth rotation angle, UT1, UTC, and UTC. The low-precision prediction of UT1, UTC for time signal broadcasts, DUT1 for deciding and announcing leap seconds, which I will come to in a few minutes. The IAU and the International Unit of Geodesy and Geophysics, both created in 1919, at the time after the First World War, when these institutions were being set up, with the IAG originating from a conference in 1962, taking its present name in 1932, and responsible for defining reference systems for Earth and space applications. All these organizations remain important. And finally, the International Telecommunication Union, the United Nations Specialized Agency for Information and Communication Technologies, the radio communication sector, is responsible for coordinating the dissemination of time and frequency signals, making relevant recommendations. That's the background and introduction to what I'm going to talk about. Now, clocks. I thought I would talk about clocks by looking at clocks I happen to have in my home, because all the parts of clocks that you will be talking about essentially exist. Now, if you look at a clock is made up of a number of parts. You have the, if I can make this work, there should be a pointer on this somewhere, I think. No, it doesn't seem to work. It doesn't matter, you can see all this perfectly clearly. All clocks, or this clock has got a pendulum, an oscillator. It has a mechanism for keeping the pendulum going, and it has a clock face. and the clock face tells the time. I will say from the very beginning, by far the simplest part of all of clocks are the pendulum, the mechanism. The clock face and time is by far the most complicated and most difficult. Now, in my dining room, I got 2 clocks. Now, the problem with having 2 clocks is making them read the same time. Now, my wife will say to me on various occasions, why do the clocks not chime at the same time? Now, there are many explanations for this. One of them is that I'm not clever enough in setting them to the right time. And she says, why is it difficult to set clocks to the right time? Well, in setting the clocks to the right time in my dining room, although they're only a few meters apart, it poses various problems. And one of the ways I do this is to set one clock with respect to my radio time signal. The other one is stopped. I then set the other one to the next time signal from my clock. I think this indicates, my idea is to indicate that setting clocks to the same time, even in one's dining room, is not a trivial operation. I have another clock, which is quite different. I have a Hamilton seagoing reference clock for navigation. And this is a clock that is much, much more accurate than either of the clocks you saw before. And this clock illustrates one of the important aspects of timekeeping, which came up in the 18th century, which rather was resolved in the 18th century. This is how to find one's position at sea. Now, this particular clock, this Hamilton reference, is one of the latest ones, and I can set it by setting it against my clock, which you can't really say, but this is a radio control clock, which links me to the world's timescales. I haven't taken the trouble to look very carefully at the qualities of my Hamilton clock. If you look at the calibration, you can't see the details, but the calibration of my Hamilton clock says that it will, in 13 days, it advanced by 2 seconds. Now, that is pretty good. Now, of course, if you want to navigate, most ships, I believe, had 3 of these, and there was a person responsible for winding the clocks. Now, I have never taken the trouble to wind my clock every day for 3 months to see by how much it really gains or loses with respect to its calibration. All I've done is with it for a couple of weeks, and it seems to follow the calibration pretty well. Now, as a matter of reference, you all know that at medium latitudes, 1 second is equivalent to just over 200 meters in terms of distance. So if you can have a clock on board your ship or whatever, boat, and you can keep it to within 1 second, then you will know your longitude to within a few hundred meters. Now, the other clock I wanted to point out, the watch. On the bottom left-hand side, there is a watch. Now, this watch was given to me a few years ago when I was in Fleurier, which is not very far from here, which was the birthplace of the most distinguished of my predecessors as directors of the BIPM, the inventor of INVAR, Charles Edward Guillaume. He studied the properties of nickel alloys in the first decade of the 20th century and invented, or discovered rather, certain alloys that essentially had no expansion coefficient, for which he received the Nobel Prize for Physics in 1920. And this watch, the case of which is made of INVAR. Now, in my office as director of the BIPM, I had a clock on the wall. This was a clock I found in a back cupboard of the Bureau International des Poids et Mesures, without any pendulum, without any case. And I had a case made, and you will see the pendulum is made of INVAR, because if you are director of an institute where previously INVAR was invented, one tends to have pieces of INVAR lying around. And this worked extremely well. I didn't make it a perfect pendulum in the sense that parts of the pendulum I didn't have of INVAR, but it kept time to within a second or so. And I'm sure on some occasions my secretary would say to people wanting to see me, depending who it was, don't go in, Terry's playing with his clock. However, I've kept it for a long time. Now, I wanted to show you just a couple of clocks because I'm very keen on Harrison's clocks. Harrison's clock H1 was the first one that was really a seagoing clock that kept time more or less sufficient to meet the requirements of the Longitude Act, which was to be able to sail over 6 weeks from Great Britain to the West Indies, not losing more than about 2 minutes. But by far the best one was what is called H4. Now, there's something interesting in H4 and the difference between H4 and H1. H1, the pendulums were moving very slowly. Those of you who have seen these clocks, which have been reconditioned, are now on exhibit at the National Maritime Museum in Greenwich. We'll see such beautiful things. You'll see they move slowly. In H4, he had the intuition that a clock in which the oscillator moved faster with a large inertia would be much better. And I think this is something which is of extreme importance. This clock has a balance wheel which moves very, very fast. Now, Harrison was an extraordinary man. He made an enormous number of inventions. I don't need to go through all of these, but he made inventions that were used subsequently for many years, or used subsequently, in the production of clocks and watches. The ultimate pendulum clock, and I'm jumping over many, many years for this, was the short clock, where you have a pendulum, a free swinging pendulum, that will then drive a clock which is out alongside it. I've taken this well-known slide. I took it from Fritz Rieler's, one of Fritz Rieler's publications, a part of it, and I've added to it my estimate of where on the same scale you would find Harrison's H4, my Hamilton Marine Chronometer, and short clocks. Now, this is a logarithmic scale, so they do actually appear all on the same slide. Now, I'm not going to talk about the primary frequency standards, optical frequency standards. This is all going to be discussed at this conference. I don't think I can add anything of great significance. But I think this gives you an idea of on the one hand, enormous improvement in accuracy. On the other hand, the remarkable things that were made before atomic clocks were invented. And I'll come back to those in a moment. Now, in looking at my clocks, I did say at the very beginning of my discussion about clocks, the problem of comparing clocks. This is another area where I'm not really going to say very much. It is clear that for medium and long distances, the fiber optic communication comparisons is by far the best. There remain problems for very long-term intercontinental distances, but this is a subject that you will be discussing. As regards the new definition of the second, again, I'm not going to say very much about this. There's a roadmap which is very difficult to read. In fact, there are two parts of it, two roadmaps. What it really means is that there's still a considerable amount of work to be done. And my personal opinion on the redefinition of the second is that probably we will not have one optical transition that is used to define the second. I think probably the definition of the second that will take place maybe 10 years from now will be one in which there are a number of alternatives that will be considered to be equivalent. Because as far as I can see, it does not look possible that one of these will stand out. But of course, who knows? So that's what I wanted to say as my introduction to clocks. Now I come to the part that is much more difficult, time. Now, time, when I showed the clock face, the clock in my home, I said time is by far the most difficult. It is once you get beyond the simple looking at time on the surface of the Earth. Now, I met Dennis McCarthy some weeks ago, and I was able to borrow one or two slides from him, which saves me the trouble of writing these out myself. This is all well known. Universal time, time measured with the Earth's rotation with respect to the sun. And the traditional definition of the second is the one I've already mentioned, 1 upon 86,400th of the mean solar day. And then you have UT1, UT0, and UT2. Perfectly clear and understandable. Then ephemeris time. Now, Felicitas showed one of these pictures, formally adopted by the IAU in 1952, and this is uniform time determined by the orbital motions of celestial bodies. Now, the tropical year of 1900, it was specified based upon Newcomb's tables of the sun. Now, there's one very important point that I'm going to dwell upon just for a moment here in terms of the ephemeris time, which is well known, and I'll come back to that in a moment. Atomic time, this is a well-known picture of Essen and Parry, both dressed in suits. Now, although I wasn't at NPL in 1955, I joined it in 1962, I don't think we all wore suits in the lab. I think this was wearing suits for a formal photograph. Now, they did something interesting. They measured the cesium, or rather, if you like, calibrated this frequency of the cesium transition, measured in terms of the second of UT2, GMT, by means of quartz clocks. And the number they got, 9192631830, was considered to represent the time linked to the rotation of the Earth at that moment. Now, there's a text that Louis Essen wrote. I will read it because it's interesting. A few months after the atomic clock had been in operation, the Astronomer Royal invited me to describe it at the meeting of the International Astronomical Union held in Dublin in 1955. Felicitas made one reference to this. One of the main subjects for discussion was the adoption of a new unit of time. Astronomers knew that the Earth was no longer adequate, and they were recommending a second of ephemeris time based on the revolution of the Earth around the Sun. Unfortunately, although this unit might be expected to be more constant than the mean solar second, it is much more difficult to measure, and the observations would have to be averaged over years to give the required accuracy. This rendered it useless as a unit of measurement, which must be available immediately. I pointed out that whatever advantages this unit might have for the astronomer, it was useless for the physicist and engineer, and suggested that since an atomic unit would be needed for the future, it would be wise to defer a decision until agreement could be obtained on the definition of such a unit. There was no such support for this suggestion, and the second of ephemeris time was adopted and was later confirmed by the International Committee of Weights and Measures, showing how even scientific bodies can make ridiculous decisions. Those were the comments of Louis Essen. And he was quite right. Why was it ridiculous? Moving from a definition of the second based on a fraction of the day to one based on a fraction of a year is just the opposite of what one needs to do to obtain a high accuracy practical realization of the second. The time of observation becomes impossibly long. You remember I referred to the advance that Harrison made in having a high-speed oscillator in his watch. In making the change, a further error was made that was well known now at least. The numerical value chosen for the length of the tropical year, 1900, was based on the average of centuries of astronomical observations, having a mean date somewhere around 1840. Now, the Earth rotation rate was known to be reducing. It's now known to be reducing mainly due to tidal friction by about 1.7 milliseconds per day per century. It's about 2.3 by tidal friction, and then another 0.5 in the opposite direction related to rebound after the last glaciation. Thus, by 1960, when the new ephemeris definition of the second was adopted, the length of the day had increased by 2.2 milliseconds, compared with that based upon the tropical year of 1900. In a year, this amounts to 745 milliseconds. The result was that when in 1967, the atomic definition of the second was adopted to be consistent with the ephemeris second in use since 1960, and this was the work of Markovich and Essen by looking at the movement of the moon, the atomic second was set to be too short, by the equivalent of about 0.75 seconds per year. So the equivalent pendulum of the atomic clock was set too short. Hence, leap seconds. this is why Essen was right. In the 1960 definition was not only was ridiculous, it was also wrong. Now, there was very strong pressure for the astronomers to maintain an astronomical definition of the unit of time. This is true from various papers one reads of the time. The relationship between the atomic time, I've not mentioned TIA, but you all know what TIA is, between TIA and UTC, in other words, the rotation of the Earth, and TIA, which was based upon the ephemeris second, is this well-known graph. The effect of the error of about 750 milliseconds per year in the original setting is shown by that red line. Therefore, this shows two things. One, that the error was made. It also shows that the measurements made by Markovitch and Essen of the ephemeris second in the 1950s, 60s was in fact actually about right. Now, if you then look at the frequency of the transition measured by Markovitch and Essen, they got this number which ends by 770, which is the one we all know. Removing the error of 2.2 milliseconds per day, the frequency of the cesium transition should be 9192631.961. Now, this is what Essen should have found when he calibrated his cesium clock against UT2 at Greenwich in 1956 by means of quartz clocks. In fact, he found 9192631.845, which is rather lower, a difference of about 1.3 parts in 10 to the 8. But this is not inconsistent, taking into account that the uncertainty of his quartz clocks is now known to be about 1 part in 10 to the 8. That, I think, is a clear explanation of the leap second, which is well known. I spoke to Dennis McCarthy about this and said, surely, at the time, people knew that the Newcomb value for the ephemeris second was biased because of this slow rate because of this change in rate of rotation of the Earth. I asked him what he thought of the explanation. He said, the only explanation I can think of is that Newcomb at the time was such a figure that no one really wanted to criticize it. Maybe. Maybe they just forgot about it. Maybe because the uncertainty was such, it was not significant. Anyway, that's where we are. There are many discussions, as you all know, what to do about the leap second. The leap second does indeed cause great difficulties, but there are strong political objections to getting rid of the leap second. One of these has always come from the United Kingdom, and it's for the reason that in the UK, GMT is the daily timescale where everyone believes that the sun is overhead the Greenwich meridian at noon. Now, it isn't exactly, and in any case, because of the equation of time, it shifts plus or minus 15 minutes either way. So there have always been strong objections, formal, strong political objections to any suggestion that the leap second should be abolished. Now, when this was last discussed before the ITU, I organized a meeting at the Royal Society in London to discuss this question of the future of the leap second, and to show the political sensitivity of this, the British Minister of Science, David Willetts, came to this meeting to listen to what was said. As you know, no conclusion came out of it. My personal opinion as to the resolution of the problem of the leap second, to enable Great Britain to keep GMT, is that one should introduce a leap minute. And so instead of the mean solar time on the Greenwich meridian averaged over a year, it will be averaged over essentially a human lifetime. And therefore, Great Britain could still keep GMT. But I'm afraid people laughed and said, Terry, you don't understand the problems. Maybe not. The Metre Convention, I don't really want to dwell on this. The Metre Convention, as Felicitas has said, is the formal intergovernmental treaty that allows decisions to be taken related to measurement units. It's the result of two conventions, 1875, 1921. General Conference of Weights and Measures has responsibility for making decisions made up of delegates of member governments. The International Committee for Weights and Measures made up of 18 individual members, and the International Bureau of Weights and Measures, the International Metrology Institute at SEV. Now, I have sat in at meetings of the International Committee for Weights and Measures for more years than I care to remember. And it is clear that the decisions of the International Committee are key to what actually happens under the Metre Convention. And what is also clear to me is that the key figures in this are the President of the International Committee and the Director of the BIPM. If the Director of the International Committee gets on well with the President of the International Committee, who is a powerful person, then it is very easy to do things, and it is very easy to stop things happening. And this, I think, is why the events that took place in the 1950s related to the ephemeris second, in fact, did not really consider all of the background. The President of the International Committee was André Donjon, who was the President of the Paris Observatory, and very clearly of the view that the astronomical definition should take place. Now, I was going to show you something from the latest recommendation of timescales from the Consultative Committee for Time and Frequency. I'm not going to show you all of the details, but the Consultative Committee for Time and Frequency is one of the committees that advises the International Committee of Weights and Measures on time and frequency. And I will simply go to the recommends. This is a meeting that took place in June this year at the BIPM, and the recommendation is the following, that the Consultative Committee for Time and Frequency recommends the following definitions of TAI and UTC be adopted by the CIPM. International Atomic Time is a continuous timescale produced by the BIPM based on the best realization of the SI second. TAI is a realization of terrestrial time with the same rate as that of TT, as defined by the IAU Resolution B1.9 2000, and Coordinated Universal Time is a timescale produced by the BIPM with the same rate as TAI, but differing from TAI only by an integral number of seconds. Now, there's nothing new in that, but surprisingly enough, this has not been stated so clearly, the relationship between TAI, TT, and UTC, and it's important that this be clearly seen as a recommendation by the CIPM that in due course will go to the General Conference. And that, I think, is, although it's taken a long time to get to this, I think this is an important decision, and I'm very hopeful that at the 26th General Conference that takes place next November, this will be adopted. And my final slide is to say something that the 26th CGPM will decide in November 2018 on the new definition of the SI. Now, this will have no significant effect on time because time is already defined by the frequency of the cesium. Going back to what was stated by the committee on the 19th of March 1791, with the new SI that will be adopted, I hope, next November, we will at last be in possession of a system of units that is not based upon any material artifact. Now, the last material artifact, you know very well, is the International Prototype of the Kilogram. Now, the International Prototype of the Kilogram is a piece of platinum, 39 millimeters high, 39 millimeters in diameter. And of course, if one had this in one hand and you drop it on the floor, it still remains the International Prototype of the Kilogram. And the joke is, if the director of the BIPM drops the International Prototype of the Kilogram on the floor and it changes its mass, it doesn't change its mass. It's the mass of the rest of the universe which changes. And this is not a thing which one should really continue. Now, we have worked for many, many years to find a way of having a unit of mass that is not based upon a material artifact. And we finally come up with the conclusion that the best way of doing this is to base it upon a fixed numerical value of the Planck constant, and at the same time, base all of the other units on fixed numerical values of a constant of nature. So we have here, you see the unperturbed ground state of cesium, no change, the speed of light, no change for the meter, the Planck constant for the kilogram, the elementary charge for the ampere, the Boltzmann constant for the Kelvin, the Avogadro constant for the mole, and the one which is slightly outside, the luminous efficiency of monochromatic radiation for the lumen, because the lumen is physiological in the sense that this number depends upon the human sensitivity of the eye. Now, another talk will be to explain the background of all of this and how it is that you can fix a constant, you can fix a unit by fixing the numerical value of a constant. It's very simple in one sense, and we've already done it with the meter. The meter is the distance traveled by light in a certain fraction of a second set by 1 upon c. The numerical value of the constant we take is 299,792,458 meters per second, and that numerical value sets the size of the meter. If you take the speed of light in terms of feet per second, you get a very different number, but the length of the meter stays the same. And if you think a little bit about this, the numerical value sets the numerical size of the meter in units depending upon the units you choose for your constant. And this we hope will be adopted. How do you realize the kilogram in terms of the Planck constant? Well, there are two sorts of experiments. One is a watt balance, where you can essentially compare the gravitational force with an electromagnetic force that's related to the kilogram through the two macroscopic quantum effects, the Josephson voltage equals proportional to E upon h, and the quantum Hall, where the electrical resistance is proportional h upon e squared. And if you have voltage and resistance, you can develop current, which gives you power, which gives you force. This is the way it's done. Not so easy to tell the general public, but I think we don't need to. Why don't we need to? Well, finally, let me say, when I was young, my telephone at home was a Bakelite column with something you picked up and you listened to it. And I remember as a child, I could unscrew the earpiece, see the magnet, see the diaphragm, and then see the wire going off to the exchange. If I take out my mobile telephone, I can't unscrew this and see what's inside because it's high science, in the same way that our units of measurement will be related to high science. They will no longer be related to mechanical objects. So, ladies and gentlemen, I've given you a quick tour of some of my views about frequency and time and other things, and I hope that I've more or less filled up the time that was allotted to me. Thank you very much.
Maybe there are questions or comments to Terry Quinn's talk.
It struck me as you were saying about the artifact that in one sense, pushing to the extreme, the time is still based on an artifact. The artifact now, though, is a single cesium atom. And just letting my imagination run, I could imagine a Isaac Asimov science fiction story where the universe is not homogeneous and cesium atoms in different parts have different resonant frequencies and therefore time would be different, in the same way as your BIPM director dropping his artifact changes the mass of the universe.
Well, I remind you of a statement made by James Clerk Maxwell in 1870. He was addressing the physics department of the British Association of the Advancement of Science, and he set out a statement in which he said that the Earth, as a standard of time, its rotation or standard of mass, could change because of meteorites falling upon it. What he then said was an atom of hydrogen, if its frequency of vibration changed by the minimum iota, it would no longer be an atom of hydrogen. Therefore, he said, if you want to base your standards on something which is permanent, use the properties of atoms. Now, his answer to your question would be, if cesium atoms behave differently in different parts of the universe, first of all, they would not in our terms be cesium atoms. But secondly, I would add, indeed, if the Planck constant is not the same in different parts of the universe, if the elementary charge is different, indeed, that changes everything. But all our knowledge of the universe, from spectroscopy of far distant galaxies, seems to indicate that what we see is consistent with our present understanding of physics. But who knows? Who knows? Certainly more stable than a piece of platinum in someone's safe.
It's difficult to see you from here. Any other question or comment? I have a comment.
No, go ahead. Go ahead.
Okay. So you said something very interesting, which has been also in my thoughts for a long time. We have a definition of the second, which is today a definition through, which was at the time the best realization of the second. You showed the roadmap, which seems very complicated, but I think that besides this roadmap and the milestones to come to an agreement maybe in 10 years, there is some conceptual decision to be made, which is how to define the second. So do you have some more comments on that?
Well, someone who's naive and not aware of the details of all of these things, I would suggest that we could do something in the same line as we have done in temperature, which I used to know a lot about. We have an international practical temperature scale, and it's been refined and refined. And in the very latest version, 1990, the latest version, there are alternative but equal realizations of T90. And I do not see, and this has never caused any particular difficulty, depending upon the instruments that you happen to be wanting to use, I do not see why we could not envisage a new definition of the second, which is based upon, for example, 3 or 4 optical transitions, all of which would have an equivalent status within an uncertainty that you would specify, 1 part in 10 to the 18. And then this would allow people to define the second to within a part in 10 to the 18 using one of possibly 4 transitions. I don't see why we shouldn't envisage something like this. Because the way things look at the moment, to me, it doesn't look as if one is going to stand out as by far the better than the others. Maybe better by a factor of 2 or 3, but I think if you wanted to choose one, it would have to be so obviously superior, and you may not arrive at one like that.
Thank you. Okay. So if there are no comments or questions, we will thank again Terry Quinn for his lecture.